In this video, we're going to talk about the terminal velocity and its relationship to the drag force. So the example says that we need to find the terminal velocity of a skydiver with a mass of 82 kilograms and an area of 0.76 square meters. And we are told that the drag coefficient for a skydiver is 1.0, and the density of air is just the standard 1.2 kilograms per cubic meter. And then we want to find the terminal velocity for this same skydiver if they were skydiving on Venus, where the density of air is 65 kilograms per cubic meter, and g is the acceleration due to gravity is 8.9 meters per second squared instead of 9.8. So the first thing we want to do is just write down some of the values here that we are given. So the mass of the skydiver is 82 kilograms. And their area, so this is just the area of the person that is actually in contact with the air. So this is where the resistance is kind of coming from. So this is 0.76 square meters. So we have a drag coefficient. This is something that is specific to the object. So in general, we have a coefficient for a person that is skydiving equal to 1.0. Now this is a dimensionless constant, so we don't have any units. And then the density of air, which is important for the drag force, is 1.2 kilograms per cubic meter. And we'll just stick to the first part of this question first. So we want to find the terminal velocity. So obviously they're moving downward toward the ground as they're falling. And this is before they open their parachute. So we want to see what the terminal velocity is. Now, we reach the terminal velocity when the person stops accelerating. So the acceleration is 0 meters per second squared. So let's look at the forces acting. So we have two forces here. We have the drag force, of course. This is an upward force, so it's opposing their movement, falling down. And then we have the weight, which of course is just mg. And the drag force is equal to 1/2 times the drag coefficient times the density of the fluid that the object is in, which of course in this case is just air, times the area, times the velocity that the object is moving squared. Now this is the terminal velocity when the weight is equal to the drag force, and we'll look at that in just a second. So we want to look at the sum of our forces as we always do in force problems. So the sum of the forces, or the net force as it is often referred to, is of course equal to mass times acceleration. Our net force here is going to be the drag force in the positive direction and the weight in the negative direction. That's equal to the mass times the acceleration. Now this is just the general equation for when something is falling and there is drag from the air. Now, what happens is the drag force is increasing as the velocity is increasing. As we can see from this equation here, for the drag force, as velocity increases, the drag force increases, and it increases up until a certain point, and that's when the drag force and the weight are equal. And that's when the acceleration is equal to 0 meters per second squared. And that gives us drag force minus the weight equals 0. And of course, we can just move the weight to the other side. And the drag force is now equal to the weight. So let's go ahead and plug in the equations for drag force and weight. So that gives us 1/2 c times rho a times the area times velocity squared, and now we are at terminal velocity because they're no longer accelerating, and this is equal to mg. So what we're going to do here is just solve for the velocity. So we're going to multiply both sides by 2 and divide by c times the density times the area, and then we're going to take the square root to get the terminal velocity is the square root of 2mg divided by the drag coefficient times density of air times the area. So now we can just plug in everything that we have. So it's going to be square root of 2 times the mass of the person, 82 kilograms, times g, 9.8 meters per second squared. This is just acceleration due to gravity. The drag coefficient, which for a skydiver is just about 1. And then the density of air, 1.2 kilograms per meter cubed, times the person's area. That's 0.76 meters squared. And when we plug this into a calculator, we're going to get about 42 meters per second. So this is the velocity at which the person stops accelerating, and they're just going to keep falling at 42 meters per second until they either open their parachute or they hit the ground. Okay, so now let's compare this to the terminal velocity on Venus, where the air is obviously much thicker, much denser. And because Venus is a little bit smaller, our acceleration due to gravity is also a little bit smaller. So let's go ahead and first we'll write down our values for Venus. That's going to be, so it's the same skydiver. So the mass and area are the same. The coefficient, or the drag coefficient, is only dependent on the object and not the surrounding environment. So that's also the same. The density of air, however, is a lot different. 65 kilograms per cubic meter. And so G on Venus is 8.9 meters per second squared. So we can use the same equation. The situation is the same. They're still falling. There's just a denser atmosphere and less gravity. So let's go ahead and plug in these different values. Same equation, different values. So we have 2 times 82 kilograms, same person, same mass. And then G is now 8.9 meters per second squared. C is the same. Density, 65 kilograms per meter cubed, times the area of the person. And this is going to give us about 5.4 meters per second. So the terminal velocity on Venus is going to be a lot slower due to that denser atmosphere and there being less gravity. And so that's how you find the terminal velocity. It is worth noting that sometimes the drag force is given as b, or some other constant, times v squared. Now, they do this just to simplify it a little bit. So in that case, b is just 1/2 c rho a times the area. So sometimes in some problems, it's different textbooks, you might find that it says the drag force is just that constant times velocity squared. It's still the same thing. They've just kind of simplified it and they'll give you a constant b that's specific to that situation. But the rest of the problem would work the same way. So hopefully that was helpful and gives you some idea of the relationship between drag force and the terminal velocity. So let me know what other kind of videos you guys would like to see, and thanks for watching.